Okay, our last form of a quadratic function that we're going to consider is factored form or intercept form. And we have an example here, and it shows why it's important, why we would need factored form or intercept form. We have a graph that represents the height of a baseball. Somebody hit a baseball into the air, hits the ground here. That's the time, how long it took it to hit the ground, and then the height at each point in time. And then we have a second player B, who hit a ball, and this equation here in intercept form or factored form represents the height of his ball that he hit. Now remember that the important thing that we can get from factored form are the x-intercepts, or the zeros, or the solutions. We had a lot of different names for those, but what they mean are the points where the parabola crosses the x-axis, and there's usually two of them. In this case there are two. One's a little bit on the negative side here, but that's why the x-intercept is important for an example like this one, where we need to know how long something stayed in the air. Okay, if we look at this graph, we can tell that player A's ball stayed in the air for about 5.1 seconds, right? Because that's the point right there where it hits the x-axis. So we need to figure out from this equation how long player B's baseball stayed in the air. So if you notice, when the parabola crosses the x-axis, just like anytime you have an x-intercept, y is equal to 0. The height is equal to 0. There's no height here or here because that's the starting point and then the ending point of the flight of this baseball. So we need to make this equation equal to 0 to figure out what time this player's baseball hit the ground. So if we do that, we know that 0 times any number is 0, right? So to figure out what value of t makes this equal to 0, we have to make this equal to 0 or this equal to 0, one or the other. So let's try that. If we have negative 16 minus 1, t minus 1 equals 0, or t minus 4 equals 0. Well, if we add 1 to both sides, do a little algebra here, you got negative 16, t equals 1. Divide both sides by negative 16. Then you get t equals negative 1/16 is one of the values that would make that height equal to 0. So that's one of our x-intercepts, our solutions. All right, what about this one? If we say add 4 to both sides, then we get t equals 4. Well, looking at this parabola up here, it looks like probably this t equals negative 1/16 would be our value that comes over here just a little before the initial value of the ball's flight. This t equals 4 must be where player B's ball hits the ground. So in this case, we can see that player A's ball stayed in the air longer than player B, and that's why we need, one of the reasons why we need intercept form. Now the problem is sometimes we are given the equation in standard form, but they want to know what the x-intercepts are. We need to know what the x-intercepts are for some reason. So we need to factor it. And we did a lot of factoring. You guys probably remember this. We used algebra tiles and some other methods. For algebra tiles, remember, first of all, we need to collect the tiles that we need. If we have a trinomial like this, 2x squared plus 4x plus 2. Remember, we had x squared tiles, x tiles, and then the unit tiles. And when we collect the tiles, in this example, there's our 2x squares, right? We have two of them, 1, 2, and then there's our 4x's, and there's our 2 unit tiles. But we have to organize those into a rectangle, and we had rules we had to follow. A long edge has to match a long edge. Short edge has to match a short edge. So there's certain rules to follow when we make these rectangles. But if we're able to do that, then it's very easy to factor the equation. We can look at this one and see that the factors would be 2x, because we go by the edge, there's x and x, plus 2, 1, 2, and then this factor is going to be x plus 1. Okay, we go by the edges when we're figuring out what the factors would be. And remember, this is how we wrote them. 2x plus 2 and x plus 1. And if you multiply those together using the box method, you're going to get 2x squared plus 4x plus 2. So we factored it, and now if we wanted to figure out what the solutions were, we could make that equal to 0, and we could solve to see what x would be in order to make those 0. So if you're comfortable with this algebra tile method, then use it. You can either use algebra tiles on your phone or on your laptop, or you can just draw them on your paper. All right, let's take a second, though, at this point to look at another example of a real-world problem that we could solve using a quadratic equation or a quadratic model. We have here a problem that says in a landscape plan, a rectangular flower bed is designed to be 4 meters longer than it is wide. And if 60 square meters are needed for the plants in the bed, what should the dimensions or the width and length of the rectangular bed be? So we like to circle our important information. It's got to be rectangular. That's a vocabulary word. Hopefully you guys all know. 4 meters longer than it is wide. And then the total has to be 60 square meters. So first we're going to draw a little picture. And this should look familiar because we did this together in class as well. Right, there's our flower bed. Lots of little flowers in it, right? Now we know that if this is the width, we're going to use W. We're told up here that the length has to be 4 meters longer. Well, to represent 4 meters longer, mathematically, we can just say W plus 4, right? Okay, and then we're told that our total area equals 60 square meters. Now, when we are finding area, remember we always multiply the width by the length. So in this case, the area would be 12. So we're going to multiply those two numbers together. So we do the same thing here. We're going to multiply this times this to get our total area. So we can write an equation over here, and it would look like this. W times W plus 4 equals 60. Okay, and then if we use distributive principle, we get W squared plus 4W equals 60. But if we want to find the solutions here, we need to have this equal to 0. Remember our example that we talked about in the beginning. So let's subtract this 60 from both sides, and we end up with W squared plus 4W minus 60 equals 0. Okay, so here's an example when we have an equation in standard form, ax squared plus bx plus c, but we want it in factored form because we want to solve it. We want to know what the x-intercepts are here. We already have it set equal to 0, and we can use algebra tiles. I just reminded you how to do those. That's fine. But we have a big number here, a 60. So it's kind of tedious to pull out 60 algebra tiles and try to organize those and figure out how we make our rectangles. So we're going to use another method that's very similar to the algebra tiles, but it's called the area model, and you guys remember this. We did a lot of these. I'm going to start out by drawing my box here. This is our area model that we used. And we always put the first term here, the W squared in this case, and the last term here. And the thing that we had to figure out was what goes here and what goes here. So this looks kind of like our algebra tile rectangle that we just did. It's just that we can just write the number negative 60 rather than pulling out 60 negative algebra tiles. All right, so the way we figured out what goes here and here is to draw the big X. And up here we put A times C, and down here we put B. And if you've forgotten what those are, how do you get those? This is standard form again, ax squared plus bx plus c. So in this case, our A is going to be 1, our B is going to be 4, and the c is going to be negative 60. So that means that a times c is negative 60, just 1 times negative 60, and then our b is going to be 4. So what we have to figure out is what we can put here, what we can multiply together to get negative 60, which when added together gives us 4. So you have to think of factors of negative 60. What kind of things can you multiply together to get negative 60? Well, one of the first things I think of is 6 times 10, and I think that's going to work here. We have to make one of them negative because we need negative 60. So if we make the 6 negative and then try that out, 10 times negative 6 is negative 60, good. Then 10 minus 6 is 4. So I think that's going to work for us. All right, now that tells us what we need to put in these other boxes up here. So we can put negative 6w here, and we can put 10w there. And now we have to figure out what our factors are based on the numbers that we determined from our x. So if we put w here and w here, remember the box method or the area model method, we multiply the numbers outside of the box together to get what goes inside the box. So we have our w and our w. Then we have negative 6w here. So what can I put here so that when I multiply w by this, I get negative 6w? Well, we don't want to overcomplicate it. It's just negative 6, right? And then we do the same thing here. What do I want to multiply? What do I multiply w by to get 10w, this w? And the answer is just 10. So those are our factors, and we can write it like this: w minus 6 and w plus 10 equals 0. And we know it works because if we multiply the negative 10 and the negative 6 and the 10 together, we get negative 60. So you want to check that. Okay? So just like we said before, we need this w minus 6 to equal 0, or we need that w plus 10 to equal 0. Well, in order for w minus 6 to equal 0, w would have to equal 6. In order for w plus 10 to equal 0, this w would have to equal negative 10. Well, we can't have a dimension, a length or a width of negative 10, so we're going to go with this one. So we know that the width is 6, and then when we add that to the 4, we find out that the length is 10, and we have our dimensions. And just to make the final connection, I used Desmos to graph w squared plus 4w minus 60, the equation we just used to find those dimensions. And look what happens. Here's our solutions, or x-intercepts, zeros, and they happen to occur at 6 and negative 10. So if they had given us a graph of this one to begin with, a graph of the function, we could have looked to see what the x-intercepts are from the graph itself.